Alright, so continuing on with the life cycle of stars, we had a picture in a previous slide, this picture, where you start off with a big cloud of gas and dust, uh, basically a nebula that contracts down and splits up into, it's almost like cell division in a sense, if you kind of look at it. Um, and we talked about just one little cluster here that turned into a star, but um, what about the rest of them? Well, pretty simple. They all turn into individual stars, and they form a star cluster. Um, and we have two cluster types here that we're talking about: open clusters and globular clusters. Um, Based on looking at the HR diagrams of each, you can immediately tell some differences. First off, typically there are fewer stars in open clusters, and they're kind of irregular shaped. Looking at the picture here, and um, most of the stars are still in the main sequence, which means that the cluster, an open cluster, at least this one anyway, is sort of young in comparison to other clusters. Whereas the globular cluster, if you look here, has way more stars. It's redder in color. These blue stars come from this end of the HR diagram. These are the bluer stars. These are the yellower and redder stars, as you can see down here. Um, and here the main sequence pretty much ends here. These stars, as we're going to discuss in this video and the next one, are dying stars. And so this cluster is globular clusters are probably in general older clusters. Uh, Young stars, hot bright stars over in like the O and the B and A range have much shorter lives. They burn through their fuel more quickly, so they don't live as long. So these stars will turn into red giants and then eventually die much sooner than the stars down here. So that's a way you can tell the age of the cluster, is looking at which stars are still in the main sequence. Over here, these stars here, you can, as we're going to see the path that they take, I'll just give you a preview. They go from the main sequence up into the red giant and back down around here, and then back up again, and then eventually become white dwarfs. You can see that stars all the way up to about G stars, F and G stars, are starting to end their life cycles. So that's the difference between these two types of clusters. Speaking of ending their life cycle, let's move right into stellar retirement. So, stars spend a good majority of their lives in the main sequence, and again, that's this branch right here. But what happens when they start to run out of fuel? What happens when all the hydrogen at the center of a star's core has been fused to helium? So this picture again, a star starts off with, from the center, the core of the center of the star, out to the edge of the star, pretty much equal balance, even balance between hydrogen and helium, mostly hydrogen, a little bit of helium. As the star fuses the hydrogen into helium, which happens at the core primarily because it's the hottest there, the amount of helium increases and hydrogen decreases, and that spreads out into the core. But it's harder to fuse helium into heavier elements than it is to fuse hydrogen into helium. You need higher temperature. So, um, while hydrogen can continue, if you read here, hydrogen can continue to fuse in the outer core, and that's what you see here. You see non-burning helium ash, they call it, meaning no fusion here because it's not hot enough, but it is still hot enough to fuse the hydrogen still out here, and so you'll have what they call hydrogen shell burning. So it's considered to be sort of stuck. That the helium here is sort of stuck until the temperature gets hot enough to fuse it, and it may happen or may not happen where the temperature gets hot enough to do that. And strangely enough, because helium isn't fusing, gravity wins. The what balances out gravity is the outward pressure from the heat in the fusion, the energy released from the fusion. And if there's no fusion process, gravity wins, and this core will start to collapse. Strangely enough, again, as it collapses, it starts to heat up, potentially getting hot enough to start to fuse the helium. So yeah, after a long time on the main sequence, the star now starts to become a red giant. So stage 7 is the main sequence, and we're on our way up to stage 9, a red giant. On the way, we are at stage 8, what's considered a subgiant. So during the hydrogen shell burning stage, here's the hydrogen shell surrounding a helium non-burning ash. The star increases a bit in size. So again, size is like, it's this dotted line is one size. This is stars on this line would be like the size of one of our suns. This little circle with a dot means our sun, so 1 solar radii. The stars on this line would be 10 solar radii, and so as you go from this line, let me draw here, from here to here, so this is like 1 solar radii, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Again, all logarithmic. It's not a linear relationship. Let me just erase this so it's not confusing. So you can see that going from 7 to 8, we increase in size. At 7, we're about 1 solar radii, if we're talking about a star like our sun. And at 8, we're probably at like maybe 7 or 8 solar radii. So we increase in size, and so you can see decrease in temperature. We go from about 6,000 to maybe about 4-ish thousand. Yeah, so due to hotter helium core, blah blah blah, the increase in pressure expands. So it's this increase in pressure from the fusing of hydrogen into helium in the shell here that expands the star out. And of course, as the star expands, it kind of dissipates, spreads out, and so the energy spreads out, and overall the temperature drops a little bit. And as you can see, it also only gets slightly brighter. Brightness is the y-axis, so to get brighter you go up on the y-axis, so we've only gone up a little bit from 7 to 8. And that's the subgiant branch. Continuing on from 8 to 9, the star reaches a point where temperature no longer rapidly falls. Instead of the temperature falling, the size of the star and the brightness, as you can see, rapidly increases. And the star becomes truly immense. So if you think about our solar system, you got the sun and Mercury, Venus, and Earth. The sun will increase in size all the way to Mercury's orbit. Huge, 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 huge. And why does a star become brighter? Because of the extreme rate of hydrogen shell burning. So as we talked about earlier, the helium ash core is collapsing, increasing in temperature. Not hot enough to fuse helium yet, but definitely hot enough to increase the rate of hydrogen fusion. And that increased rate of hydrogen fusion is like, bam, screw you, gravity, I'm going to push out and make you as big as a red giant up to Mercury's orbit. Alright. And then, from here, the mass of the star determines what happens. Technically, that's the case in all aspects of the life cycle of a star, but there's really truly a branch off, and you can go to different directions from 9 on. If the star is much smaller than our sun, gravity is too weak to contain the expansion, and the outer layers of the star drift out into space, leaving behind a collapsed helium core. It might look something like this, even though these pictures are for later on. But it might look something like this, where you have your helium core, and then the outer layers just go poof, because gravity can't hold on to them. Stars similar in size to our sun have enough mass that gravity can squeeze the helium core, finally, to the point where its temperature becomes high enough to fuse helium into carbon. And carbon is a very special element. From here, complex processes in the core, which I won't go into, bring the star to stage 10. And as you can see, stage 10 is hotter, because it goes that way on the x-axis. It's dimmer, because it goes down on the y-axis. and it's smaller because it goes from like the 100 solar radii line to the 10 solar radii line, so it definitely gets much smaller and less bright and stable as it fuses helium into carbon at the core and hydrogen into helium in a shell around the core. I'm not really going to go into the horizontal branch too much. Don't want to go into too much detail here. So, moving on. The path from stage 10 to 11 is very similar to that from 8 to 9. So from 8 to 9, as you saw, we had hit basically a stopping point where we couldn't fuse helium into the next heavier element, carbon, and so the helium core was shrinking, greatly increasing in temperature, expanding out um, the outer layers of the star from 8 to 9. Same thing here. Now we got carbon, which the star is not hot enough to fuse carbon, but it is hot enough to really increase the rate at which hydrogen fuses into carbon and helium fuses into carbon and hydrogen fuses into helium. And again, that's going to increase the temperature, decrease the temperature slightly. It's actually very slightly. They call this like the vertical part of the branch, where temperature doesn't change much. It's the size and brightness that changes. So the size will increase, even bigger than before, and the brightness really increases. So 11 and 9 are sort of basically the same points in the life cycle. It's just that this is when helium finally begins to start fusing, and this is when potentially carbon could fuse. If you look at this picture, we could just keep on going. So we got hydrogen fusing into helium, this little orange. Here we just got hydrogen, some helium, no fusion taking place here. Here in the red we got carbon fusing in helium fusing into carbon. In this light blue we got carbon fusing into oxygen, if that's possible to happen, and oxygen fusing into neon, etc., etc. So how far this goes, how many shells you have, depends on the mass of the star. The more massive the star is, the more shells you can have and the heavier elements you can fuse. And so if it's a star like our sun, this is it. This is the end of the road, and we'll talk about that next. But just real briefly to end this video, once you hit iron, that's it for any star. It doesn't really matter your mass, because iron is a special element. It's the most stable element in terms of number of particles in the nucleus and mass per nuclear particle. You can see hydrogen is here. This is atomic number, so if you look at the periodic table, it just goes in order: hydrogen, helium, lithium, straight through to the heavier elements. Iron is the lowest. It's really cool. Elements on this side of iron, they give off energy when they're fused into heavier elements, and it requires energy to split them up into lighter elements. So why a star works is because it doesn't require energy to fuse. It just actually, in fact, as it fuses, it gives off energy. That's why stars are so hot and bright. But once you hit iron, it would actually require, or elements heavier than iron, it would actually require energy to fuse them. So elements on this side, it requires energy to fuse them, and it gives off energy to break them into lighter elements. So that's why on Earth we use these elements in nuclear power plants and, unfortunately, nuclear weapons. As we split atoms like uranium or plutonium, whatever, into lighter elements, they give off energy, and then they can power homes or destroy cities, depending on your use for them. So once a star hits iron, the star's not going to get extra energy. There's only so much energy stored in each atom, and so this is the end of the road for any star. Very interesting phenomena. If you're interested in this, I would look into this into more detail. But it's really cool, this property of elements, and how iron for some reason is the, well, not for some reason, if you're a chemist you probably know it much better than I do, but for me, for some reason, iron is the lowest, most stable element in the periodic table. Pretty cool. Alright, so I'll continue on with the end of the road for a star like our Sun, stage 12 and beyond, in the next video.